welcome to the deep dive. Today, we're jumping straight into, well, a pretty epic story, actually. How our own galaxy, the Milky Way, got to be the way it is.
Yeah, and it's not just a gentle process, is it? We're talking about huge collisions, galactic scale smash-ups.
Exactly. The current thinking is that these massive galaxies like ours, they're basically built from the wreckage of smaller ones over billions and billions of years.
Mergers.
Cosmic recycling on a grand scale. Little galaxies get pulled in by gravity, they get torn apart,
Yeah.
and their stars kind of get mixed into the bigger system.
And today, we're really zeroing in on one specific, really significant event in our Milky Way's past. The collision with a smaller galaxy that scientists now call Gaia-Enceladus.
That's the one. It seems to have been a really major player in our galaxy's history.
Right. And we've been looking at some really interesting research here, particularly this document, Perryman Gaia-015.pdf, which goes into the evidence, the breadcrumbs left behind by this Enceladus galaxy.
And how scientists actually managed to piece it all together, which is an amazing story in itself. Totally. So our goal here is to unpack that evidence, understand how this ancient crash was uncovered, and, what it did to the Milky Way, how it shaped what we see today.
Yeah, there are some pretty surprising consequences, actually. It really changed our galaxy.
So get ready. This should give you a much clearer picture of, well, where our galactic home actually came from.
Okay, so maybe before we dive headfirst into the collision itself, it's worth just quickly sketching out the Milky Way's basic structure. Just a reminder.
Good idea. So you've got the bright bit in the middle, the central bulge,
Right, packed with older stars mostly.
and then the big, flat, rotating part, the disk. That's where we are, where most stars we see are.
And that disk isn't just one thing either, is it? There's a thinner component and a thicker one, kind of layered.
Yeah, thin disk, thick disk, and all of that bulge disk, it's all embedded in this enormous, much more spread out region called the halo.
Which is mostly, well, we think it's mostly dark matter,
Yeah.
right? But it also has these scattered older stars.
And that dark matter halo thing is important, isn't it?
Yeah.
Because that's kind of the cradle where the first galaxies and stars started forming way, way back. The gravitational anchor, sort of.
Exactly, that's the scaffolding. So, okay, that's the basic layout. But how on earth do you find evidence of a collision that happened, 10 billion years ago? Where do you even look?
Yeah, what are the clues?
Well, the stars themselves are the key witnesses, specifically how they move and what they're made of their chemistry.
Okay, so how they move.
Right. So stars in the disk, like our sun, they tend to orbit the galactic center in a pretty orderly fashion. They go round and round, maybe bobbing up and down a bit.
Like horses on a merry-go-round, kind of?
Sort of, yeah. But halo stars, they're different. Their orbits are often much wilder, more elongated, sometimes tilted. They can zip through our part of the galaxy at really high speeds.
And the chemistry part. You mentioned metal-poor stars earlier.
Mm-hmm.
What does that mean in this context? It's not literally less iron, is it?
Huh? No, not like less scrap metal. In astronomy, metals means pretty much anything heavier than hydrogen and helium.
Ah, right. Carbon, oxygen, iron, all that stuff.
Exactly. And that stuff is cooked up inside stars and then scattered when stars die, in supernovae and things. So stars that formed really early on, before many generations of stars had polluted the universe with these heavier elements.
That have less of that stuff. They'd be metal poor.
Precisely. And that makes them markers for old populations. The sources mention Barnard's star. You might have heard of it.
Yeah, it's famous for moving really fast across the sky, isn't it?
It is. It's got the largest proper motion, that apparent movement of any known star. And guess what? It's metal poor and seems to be on a halo-like orbit. It's ancient, maybe 10, 12 billion years old.
Wow. Compared to our sun at, 4.5 billion?
Yeah, our sun's a relative newcomer. So Barnard's star is like this relic from the early days just passing through our neighborhood.
That really puts things in perspective. Okay, so we've got stars moving differently and stars with different chemical makeups telling us about age. How does that connect to galaxies smashing together, these stellar streams?
Well, the idea is if the Milky Way grew by swallowing smaller galaxies, then the remnants of those meals should still be around, particularly in the halo.
Not just smoothly mixed in.
Probably not completely, no, especially for the bigger meals. Models suggest the inner halo, the part closer to us, should be dominated by debris from just a few large early mergers.
Okay.
So imagine a smaller galaxy falling into the early Milky Way. Its gravity isn't strong enough to hold it together against the Milky Way's pull. It gets stretched.
Like spaghetti. Tidal forces.
Exactly, tidal disruption. It gets pulled apart into long streams of stars following roughly the path the original galaxy was on.
So like cosmic breadcrumbs tracing the path of the victim galaxy.
That's a good way to put it. And even after billions of years, maybe multiple orbits, those stars might still be recognizable.
How? If they're all spread out.
Two main things. They might share a specific chemical signature, a fingerprint inherited from their parent galaxy, which could be different from the general Milky Way population.
Okay, the chemistry clue.
And, crucially, they might retain a memory of their original motion. Even if they're scattered across the sky now, their velocities, their speed and direction might still show they were once part of the same group, moving together, a common angular momentum.
Fascinating. So they're like a ghost moving through the galaxy, even though they're spread out.
Kind of, yeah. Their collective motion gives them away.
Were there hints of this before all the latest data? Did people suspect this was happening?
Oh, absolutely. It wasn't a totally new idea when Gaia came along. Earlier surveys looking at star velocities and chemistry near the sun had already found groups of stars that looked, well, out of place, like they didn't quite belong to the main disk or halo populations.
Intriguing.
Yeah, the document actually mentions a specific discovery back in 1997 using data from an earlier space mission called Hipparcos. They identified what they called a disrupted event based on stars moving together in a peculiar way. So the concept was definitely there.
But it sounds like things really kicked into high gear more recently. The evidence became much stronger.
Massively stronger. Data from things like the Sloan Digital Sky Survey helped, but the real revolution was the Gaia mission, especially its second data release, Gaia-DR2.
Gaia. We hear about it all the time. What made it such a game changer for this?
Just the sheer precision and volume of data. Gaia measured the positions, distances, and crucially, the tiny motions across the sky for over 1 billion stars. With incredible accuracy.
1 billion stars. Okay, that's a lot.
It's staggering. And with that data, astronomers could suddenly see patterns that were totally invisible before. They looked at things like color magnitude diagrams, ways of plotting star brightness against color, and saw distinct sequences, groups of stars that stood out.
Different families of stars almost.
Yeah, exactly. And perhaps even more importantly, they found this huge prominent structure in the way nearby halo stars were moving. A big group, all moving in a related way.
And what was special about their movement?
Get this. A large chunk of them were moving slightly retrograde.
Retrograde, meaning...
Meaning they were orbiting the Milky Way backwards compared to the general rotation of the disk and most other stars.
Whoa, okay, that is weird, like swimming against the current.
Precisely, and that immediately screams outsider. It's very hard to form stars within the Milky Way that end up going backwards like that. It strongly suggests they came from somewhere else, probably a galaxy that fell in on a retrograde orbit.
The smoking gun you said earlier.
Pretty much, yeah. That retrograde signal was huge.
So this group of backwards moving stars that led directly to identifying Gaia-Enceladus.
It was the key piece of the puzzle. A big study in 2018, led by Amina Helmi and her team, used that amazing Gaia-DR2 data to really dissect the motions and properties of stars in the inner halo.
And they found...
They found that a huge fraction of the inner halo isn't just a random mix of old stars. It's dominated by the debris from one massive accretion event, one big merger.
Wow. One main event shaped so much of it.
Yeah. And they estimated the galaxy that fell in was pretty hefty, maybe even a bit more massive than the small Magellanic Cloud, which is one of the dwarf galaxies orbiting us today.
So not a tiny galaxy then, a significant one.
Definitely significant, and that's the object they named Gaia-Enceladus.
Gaia-Enceladus. Okay, why that name? I mean, Enceladus is a moon of Saturn, right? Famous for its geysers.
It is, and that caused a bit of confusion initially. The name actually comes from Greek mythology. Enceladus was one of the giants, son of Gaia, Earth, and Uranus, Sky.
Ah, mythology, okay.
Yeah, the story goes he was defeated by Athena and buried under Mount Etna in Sicily, causing earthquakes whenever he stirred. So the name connects Gaia, the source of the data, with this giant mythological figure. It's meant to evoke something large and buried within our galaxy.
Got it. Helps distinguish it from the icy moon, Gaia-Enceladus, the buried giant. So what else do we know about its stars and the merger itself? What are the characteristics?
Well, the stars identified as being from Gaia-Enceladus are now found pretty much all over the sky. They're not confined to one small area.
So they've really spread out over the last 10 billion years.
Oh, yeah. Totally mixed through the inner halo. But their motions still betray their origin. They show those characteristics slightly retrograde and quite elongated or eccentric orbits.
And it's not just individual stars, right?
Yeah.
Didn't they link other things to it?
Yes, that's another remarkable part. Hundreds of RR Lyrae stars, These are specific types of pulsating stars that are great for measuring distances and are typically old, have been linked to Gaia-Enceladus based on their orbits.
Hundreds.
And, maybe even more strikingly, about 13 globular clusters.
Globular clusters. Those ancient, dense balls of stars.
Exactly. 13 of them seem to share the same orbital properties and also have ages and chemical compositions consistent with being part of the Gaia-Enceladus system before it merged. That's pretty compelling evidence.
Wow. Linking whole star clusters to this one event, that really paints a picture of the scale. So, smashing something that big into the young Milky Way must have had huge consequences. What did it do to our galaxy?
It really shook things up. The estimate suggests the mass ratio was maybe around 4 to 1, the young Milky Way being 4 times more massive than Gaia-Enceladus. That's a major merger, not a minor nibble.
Okay, 4 to 1. Big impact.
Huge impact. The prevailing theory is that this collision caused what astronomers call dynamical heating of the early Milky Way's stellar disk.
Dynamical heating. Sounds energetic.
It is. Think about stirring a pot vigorously. The infalling galaxy's gravity and the resulting chaotic motions essentially pumped energy into the existing disk stars. It made them move faster, pushed them onto more inclined and less circular orbits, puffing up the disk vertically.
Ah, so that's where the thick disk comes from. This merger puffed up the original thinner disk.
That seems to be the leading hypothesis, yes. This merger, happening around 10 billion years ago, effectively transformed the early, probably thinner disk into the thicker, hotter component we see today, the galactic thick disk.
So a major part of our galaxy's structure is basically a scar from this ancient collision.
A scar, or maybe more like a consequence, yeah. And the thinking is, this was likely the last really significant merger the Milky Way experienced. There have been smaller ones since, but this was probably the last big one.
Incredible. And is this just something we infer from looking at the Milky Way, or does it fit with broader ideas about how galaxies form?
That's the really neat part. It fits beautifully. What we observe in the Milky Way lines up incredibly well with what large-scale cosmological simulations predict.
Simulations, like computer models of the universe.
Exactly. These incredibly complex simulations, like the ones from the EGL project, try to model the formation and evolution of thousands of galaxies from the early universe right up to the present day, including gravity, gas physics, star formation, dark matter, everything.
And they see mergers like Gaia-Enceladus happening in their simulated galaxy.
They do. A study by Bignon and colleagues specifically looked through the EGLE simulations and found simulated galaxies that underwent mergers strikingly similar to Gaia-Enceladus.
Oh, similar in what way?
Well, they found a simulated merger happening around 9 billion years ago, pretty close to the estimate for Gaia-Enceladus. The debris from the simulated merger also ended up on retrograde orbits. The merger triggered bursts of star formation, it dynamically heated the disk, creating a thick disk, and it deposited lots of debris in the halo.
Wow, that's remarkably specific. The simulation basically predicted what Gaia then found.
Or perhaps it showed that the kind of event Gaia found is entirely expected, even common, in the standard picture of galaxy formation. The level of agreement is really quite stunning. It gives us a lot of confidence in the whole picture.
So it suggests our Milky Way's story isn't necessarily unique, but maybe typical for how large spiral galaxies grow up.
That's certainly what it looks like, yeah. These major mergers in the early universe seem to be a key part of the process.
It really shows the power of combining these different approaches, doesn't it? Pinpoint observations from Gaia and these huge theoretical simulations pointing to the same story.
Absolutely. It's a triumph, really, for modern astrophysics. Being able to piece together this kind of detailed history from billions of years ago, it's incredible.
Okay, so let's try and wrap this up. If we had to boil down the main message from this deep dive into Gaia-Enceladus, what would it be?
I think the core takeaway is that our Milky Way isn't pristine. Its current structure, especially the thick disk and a big chunk of the inner halo, carries the very clear imprint of a massive collision that happened about 10 billion years ago with this Gaia-Enceladus galaxy.
And we figured this out by looking at basically how stars move and what they're made of.
Exactly. Those incredibly precise measurements of stellar motions and chemistry, mainly thanks to Gaia, were the key observational breakthrough. And crucially, this observational story is backed up strongly by cosmological simulations that show similar events are a natural part of galaxy formation.
So these subtle details about stars in our own galactic backyard are actually fossils, telling this incredibly violent and dramatic story about our origins.
That's precisely it. Fossil evidence written in the stars.
It really does change how you think about the galaxy looking up at night. It's not static at all. It has this incredibly dynamic, even violent history.
Absolutely. And, it leaves you with a pretty compelling thought to chew on. Well, given that we've uncovered this massive event, the Gaia-Enceladus merger, relatively recently,
Mhm.
what else is hiding in the data? What other maybe smaller merger events or ancient interactions are still waiting to be found within the Milky Way?
Hmm. More galactic ghosts out there.
Maybe. It just highlights how much we're still learning. Ongoing research, future telescopes, they're constantly peeling back more layers, refining our picture of the cosmos and, our own place within it. There are probably still plenty of secrets locked away in the stars.